Hi everyone, thanks for joining and welcome to the second session of the new 102 working stream at this year's event. My name is Chris, I'll be co-chairing with David Lee. Just a little bit about the stream if you weren't on yesterday's introduction into system information session with Dave. It was created to follow on from the existing 101 working group for the purpose of providing a more in-depth look into all things IBM-Z related, focusing on more specialized areas and going into a bit more detail on topics that might have been introduced within the 101 stream. It's ideal for anyone with a couple or more years experience on the platform, or for anyone interested in starting to learn a bit more about other areas that they may have not had much exposure to in the past. This session is Disk Storage 102, a local real world example with a bit of GDPS being delivered by Simon Fairborn. If you do have any questions throughout, please feel free to just use the chat window and we can pick these up for Simon at the end of the presentation. So Simon, if you could introduce yourself and just kick off your stream, kick off your session whenever you're ready.
Right, so you mentioned the charity raffle that was definitely there in the template. So, right. Oh, no, you prefer. Right, okay then. Well, hello there. Yes, I'm Simon Fairborn. I've been on the mainframe about 16 years now, so counting that as being reasonably new still. It does take a long time to get up to get fully up to speed, just about getting there. Almost 16 years on the mainframe. Have been at Nationwide Building Society. I imagine you will know who and what that is. If you don't, well, that'll be an interesting first question. It's fair to say, probably heading towards the end of my my career, full stop in computing. I've tried various things in various platforms, etc., and mostly trying to avoid following my father's footsteps, that sort of thing. Anyway, enough about me for the moment. Why this particular session? Fair enough. Well, our Chris, who just started things off here, recalls a particular session we did internally at Nationwide, where some explaining was needed because people were getting very confused by various bits. So I had a whiteboard and a load of people in a room, and I draw an awful lot of blobby diagrams. And blobby diagrams do sort of help. Now, an awful lot of that was very specific to Nationwide and how things evolved there. And I can't go into too much detail on that specifically. However, some of the general principles that were touched on there will hopefully be useful to you all in your own shops, wherever that is. Got to have a bit of a caveat that the whole subject of disk storage, etc., is absolutely massive. It's too much to cover on one session, so I have to gloss over bits in places, but hopefully get some sort of general ideas to add to your knowledge base, and that'll be useful. Okay, 101 assumptions. I attended the 101 session early in the week, and that was interesting. There was relatively little mention of disk, which slightly surprised me. There might be another session around there, so I just hadn't caught. But yes, I'm going to assume you're starting with roughly that sort of knowledge level. But so yeah, as it says in the bullets there, we've got flipping great big disks and flipping great big processors, hopefully talking to each other in sensible ways. Yes, they're I'll say linked together with all sorts of interesting glorified string, and that is another issue I'm not going to cover today. We just have to accept for the moment there are channels that go from the one to the other. We're not going to worry too much about how that works. Similarly, a lot of storage is nowadays hidden from anyone who's developing on it or sort of working with it much, because we now have SMS covering most of the relative bits through the routines that it has. Again, SMS is not an area I'm going to be covering today either. That's an awful lot I'm not covering today, isn't it? Right, anyway, I'm going to move on a slide. That's not going forward. That's unfortunate. Why are we not going forward? Oh well, be hard to do that. Right, so as a basis of sort of things I'm going to talk about, I'm going to mention what we have at Nationwide now. Again, I'm going to have to be very simplified here and talk about just one of the systems we have. We have quite a few, as is probably fairly normal, but by far the biggest we have is the one that supports the SAP core banking platform. It's big, it's growing, it's quite scary in places, but it's giving us a job which is useful. Now, one of the key things I want to mention at this point is that the SAP area follows the classic three-part or three-tier application development format. So we got a presentation layer out there. That's normally web browsers and that sort of stuff, what people actually look at. That's not on Z. We've got that talks to a whole load of business logic. Well, effectively sort of serves things out to clients nowadays. It used to be application programs, but that's changing as fashions in IT change. And again, the business logic is on a different part of the system. So again, I'm not going to touch that. But at the heart of everything, right at the back end, is an awful lot of data. And the data absolutely sits on Z. It's primarily, from our point of view, on IBM's DB2. As for the database, there are other bits, flatter elements as well. One of the key bits we have is that all the data for the whole environment, for the whole solution, comes back to the same set of disks, which is why we're relevant for what we're talking about in terms of disk. So yeah, so it means, I'm getting ahead of myself. I'll talk about being able to keep everything consistent more later. But yes, goes on to Z for the very good reason that IBM scales like anything. And so we're able to build a system that's able to grow, and it has grown. Right, moving forward. So the way we've done it, does that work any better? No, it doesn't. That's better. Remember, I've got to click on the wrong window to be able to do that. Never mind. Here we go. So expanding a little more. So because as you can imagine, core banking is pretty darned important. We have what's known as a GDPS foresight solution. So effectively, I mean, oh, sorry, I'm going to get some water. It gives me both a DR solution and a HA solution. So disaster recovery, if we lose one whole sort of site, etc., and high availability if we lose bits within that. Excuse me. So I'm not sure how much detail. Have we got any questions in so far? That's good. Okay, fair enough. So you can see the slide here. We've got two major locations. Again, I'm not going to name them, but within those locations, we've got sort of virtual sites. Now, I haven't put any of the interlinking between the sites in here because it's not entirely relevant. We just, for the moment, just accept that's what we've got. I'll break down what how the DR and HA sides work in a moment. Okay, before we get too much further, one of the things I do want to cover is a bit on really basic disk stuff. So we forget Z for the moment, just for a moment, it won't be for long. What we have is some that effectively evolved over a lot of time. With the 101, that was saying how the System 360 was announced in 1964. And one of the big features was always having backward compatibility. And I think that's effectively also affected the way the storage boxes have evolved as well. So if you think back to really old disks, loads of other things churning around quite a lot, and then going through control units, and then those units are being served back into the mainframe itself. I should be following my own notes rather than improvising, should I? We have IBM disk, the DS8K frames. This is not unusual. Other vendors do supply stuff. I don't know if anyone's on from any other, but they are certainly about. The other frames are at least generally similar, but they're well, they can explain the differences. I'm sure they will. Right. One of the key things now is they need to consider there are, from a numbering perspective, certain numbers of controllers and disk within that. And I get ahead of myself. 256 controllers, which you can then talk to. Again, nowadays they're a bit of a logical thing. They were very much sort of physical lumps. Nowadays, everything is virtualized through through software, so you don't have to worry about that so much. Within those controllers, you get another set of you get 256 devices, theoretically, and they each sort of effectively represent a lump of spinning disk. Now, in practice, it's not spinning disk anymore; it's all effectively memory. But because of the backward compatibility, you've got to have the ability to have it behave as if it was spinning disk. Anyway. So as a result, when we're talking to disks, yes, we give them device names. I'm not going to touch on names much. It's just a way of describing something that's slightly more meaningful. In disk storage terms, what you're really interested in is the I know it comes to 5 in a minute, but a 4-digit device number, as I say, XXYY, where 1 refers to the control unit within the DSOK, or 1 refers to the device within that control unit. I'm going to move on again. Will it let me? Yes, got it first time this time. Lovely. Okay. What's going to go? Why don't I come to this one first? Right. Some of the techniques involved in accessing the disk very much come out of history, even now. What I'm going to sort of demonstrate is the idea of how a disk used to work. I mean, you can imagine, have you seen the inside of a disk? So they've basically got a great big platter going on there, going around several times, really quite fast nowadays. It was slower before. And what you've got is a little head going across, not actually touching anything, not like a gramophone record used to and still does. But you've sort of got the thing going spinning around, and if you can see me on the video camera, I've got to have a virtual finger across there, sort of tracking across the idea of a plane of where some disk is. And what it has to do is work out where it is a lot of the time. Oh, hang on, this one's it'll be slightly less exhausting. So let's say we're looking for track number 64. So it's going to check it. Right, we're over at 0 at the moment. Let's chuck over here. Where we got to? We're about 37. Okay, we haven't gone far enough. Goes over, reads a bit more. How far have we got to? 75. Oh, overshot. Go back a bit, and eventually it finds number 64. Again, historically. However, that's this whole over and undershooting is a historic factor that's involved. In the meantime, the application's waiting for all this. This takes a certain amount of time. So it's why you tend to program things around. Okay, send the disk request off. Okay, we'll park the CPU and go to some other stuff in the meantime and wait for the disk stuff to come back. So bearing in mind that takes a long time. So having had this sort of check going on along that, having read the data and discovered you don't necessarily need it, you don't necessarily also throw it away. So yeah, so when you oh, hang on, I wasn't going to come to that. Oh, I've got ahead of myself. If you've got some memory in your controller, which was like a new thing once, it's all memory now, but what you do is remember, well, okay, we know what track 27 was. We'll just hold that for the moment till we know we don't need it. This comes into practice lately. I need some more water. Anyway, at some point you can reach your track number 64 that I mentioned earlier on, and you think that's a really handy place to be. So you've moved along here to where your track is. Now, one of the things that I quite like is when they discovered, okay, we know where we are, right, so our track's in the right place, lovely. Okay, if only we had another way of making other tracks in the same place to increase the amount of space you've got. So imagine, oh, hang on, you got a track under here and a track under there, and they're all at that position number 64. You could get even more data once you found your position. That's where you get the tracks actually being stacked physically, and that's where we get the concept of a cylinder, because there's 15 of these. A bit of history for you. Anyway, moving on. So one of the other factors coming along was if you know you want track 64, you may just think, well, okay, let's move on to the next one just in case 65 is what they want. So you get programs are being built to allow for the fact that it might do things in sequence, and you get more and more sort of programming around making things efficient. Now, we don't tend to bother now because everything's an awful lot faster, but this thing was possible. But this also increased the idea of there being more memory used. Memory became more and more useful. And So yeah, more and more memory got put onto the controller. Memory got cheaper, so more and more memory went onto the controller. So eventually thinking, well, okay, if we've got it in memory, do we have to wait to actually write the disk again? Well, no, you don't necessarily. This is where battery backing came in. So right, if you're reading, it doesn't matter so much. But if you're writing to a disk, well, okay, you really want to say, no, I don't want to say it's totally written until we've seen it actually on that disk. Well, that's fair enough. Then you reach a stage, well, okay, if we can guarantee that the write is going to be okay, even though we've written to memory, haven't actually written it yet, if we have enough guaranteed time that if we lose the power, some batteries will just make sure that that write has happened, we can say it's happened. And that's one of the things that's one of the reasons we have massive great batteries in the bottom ends or top end, wherever it is, of the disk units. This allows time for everything that's in memory to be able to be written down onto disk, so you get into a safe state. Because memory's volatile, disk not so. So right, where was I going with that one? Okay, writes can be in memory. So because you're doing things into memory, that makes things even faster. And because it's mainframe, an awful lot of things need to be faster. That's all good. Right, okay. So the final thing, as I mentioned on this particular section, is around parallel access volumes. So again, now you're talking about a memory model rather than necessarily where the heads on that disk are. Why was you can have more than one conversation to that disk at the same time, because you're not actually waiting for the read heads to find that track number 64. If you've already got something in memory over there and you've got other bits of memory from over there, you can actually have parallel sort of reads and writes, and this is where parallel access comes in. The problem is when you're going back in time, well, it was only ever designed to be able to cope, but each channel programmed to each device was only able to designed to be able to cope with one operation at a time. This is where you get the idea of, well, okay, if we had some virtual addresses that say, well, they know they're going to be this volume, but they're going to take a sideways route, something like that. Basically, we can read and write in parallel. That's how I get parallel access volumes. They can impersonate real devices. Now, on the DS8K, they're called aliases. Of course, they're not called the same thing. On Z, we call them parallel access volumes, and they are very useful things and speed things up. So, right, okay, I hope I find any questions come through yet, Chris, or am I rattling away with that?
Nothing yet.
Nothing yet. Okay, fair enough. I shall just keep on going then. Right, returning to the Z briefly. As we described now, there are controllers and devices in there. That's all good. So one of the key things is the Z doesn't necessarily have to have the same set of numbers. So I've already written that there. I'm not going to do death by PowerPoint only if I can help it. But quite literally, in the example there, a 1, 2, 3, 4 could actually theoretically map to a completely different number. Now, in practice, you better have a good reason for that, because it's going to be really confusing when you're talking to people who are looking after different bits of kits in different areas. If you start using a different number altogether for when you're talking about a particular device, it's going to get pretty confusing. So, yeah, what else am I going to call on that? Right, one of the other things, and the key bit for Z is, I would say splitting and ranges is what I've called it here. I could walk through this example a little bit. So we got two disk frames, A and B. This is all good. You can see we've got a partition over on the left here. I can't point. Can I point? Does that work? I don't know if you see my mouse there. Maybe you do. Anyway, so you got a blue partition. We call that blue LPAR. We certainly covered that one in the 101s. So you get an LPAR that's talking to a disk frame, so it's seeing everything on controller number 10, all the way from 00 to FF, at least theoretically. And that's all very well. Similarly, over the right-hand side, we've got this green area, vert, because we can get green into 4 letters, talking to the B. Now, you also then have a situation where you could have a different partition where it's talking half to one frame and half to another. Now, so for a given range of devices, in this case, so you can see the 10,000 range through to 10.0FF, where it actually goes to for that information doesn't have to be the same. It doesn't have to be the same across the whole estate or anything like that. So yeah, with this example, you got the top half is going to one disk frame, the bottom half of it going to another disk frame. Yeah, just looking at my notes there. I think I've covered everything I was intent to put in there. Now, this could be quite useful with. Move on to the next slide. Just because you are not seeing, or you haven't got the full half of that disk available on the middle partition over there, that doesn't mean it's not necessarily not unavailable. So what I'll mention here is there is a fifth digit that's appeared now, that the lead thing, which can be used for certain things. Now, ZOS application program, because history, etc., needs that 4-figure device. That's not going to change. But some of the other aspects don't necessarily need to have that set of 4 figures. So we can start using that fifth, that leading one. One of the options I mentioned here is parallel access volumes or aliases. So if you happen to have your aliases taking up a low, again, with this one, you could theoretically have 124 real volumes, and you have 124 parallel access volumes. So everything is effective. We've got double a second route to every single device, and even better, it can move around and decide what it's going to go to. And every single one of those can be available as long as you move things out into an appropriate place. Now, the frames can only cope with 256, so you haven't got that extra number. The frames have to show that the devices are in a 4-figure format, at least at the moment. So, for example, with the A frame that we've got over there, 1080 to 10.0FF could theoretically be all parallel access volumes. So your blue partition, seeing half of them on as data and the other half as paths. Similar thing over on the right hand side, but that middle partition actually gets, for that range of devices, for anything starting roughly 10, it's going to get all the data volumes and a whole load of parallel access volumes, because parallel access volumes can use that extra digit. Now, there are various other functions that use that fifth digit, not just paths. Some of the replication technologies that come up, I think, can be put over there. We don't, so I don't know too much about it, but there are certainly ways of using that extra digit. This is just a theoretical example. We don't do all the paths for various good reasons, because it isn't actually as performed as it might appear to be. So we don't do that. Right, moving on. But anyway, one of the key things we want to be mentioning here is the whole idea that you need to be sometimes a little clever with what you do with numbers. If I'm going to go through to the next slide, which is all about numbers. So that wasn't the one I was expecting next. Oh, never mind. So yes, being able to use the numbers cleverly is a really sort of important part, certainly what I do, and is why I had ended up with that whiteboard that I mentioned earlier on with the meeting with Chris. Right. Anyway, so what I can do there? Yes, one of the I've got loads of notes here. I forgot to read. Silly me. Right. One of the key things that come up with having large databases is you end up using an awful lot of UCBs, or the control blocks that talk down to the devices. For the application, as I said, you've only got the 4 digits at the moment to be able to deal with. So you've got a maximum of 0000 to FFFF. That gives you 65,536 device numbers, theoretically. However, you don't get all of those, which is slightly awkward. So before I can get too far on the disk front, there are other things that also need to use those numbers, things like consoles, comms devices, tape drives and stuff like that. You bound to have those as there. There are also some odd virtual devices that get created around the high F side that I just tend to just leave a bit of space for and ignore for the moment. Anyway, the next few slides I'm going to handle the way we look at a particular device. It's going to be, for example, a DB2. I'm not going to say what it's called, but again, this is all theoretical. What you could do with a single device and what happens to it to be able to provide all the HA and DR stuff that I mentioned earlier on. So yes, to keep the example going, so we're going to have a device 1000. Now you just imagine, of course, everything else in 10 is probably also related to DB2, but if you just keep to a single device, it probably keeps things simpler. It might be just as well. So high availability. Just to check everyone's happy about what high availability actually means in practical terms. I'll assume we sort of have some sort of idea on what. But looking at the diagram here, the idea is we can lose any lump of that. We lose either of the Zs in either a site, theoretically, either by mishap from ne'er-do-wells or whatever, or by simply planned maintenance. We do this on a regular basis. We're taking the partition out. It just continues working. Not a problem there. Similarly, you can theoretically, theoretically, no, it does actually work. You could lose whole frames and things just keep going. I'm going to have to explore some more of that, but in the meantime, basically, you can lose any single composer, and in fact, you can lose a whole site, and everything keeps going. We're in the banking sector. Basically, everything has to just keep going. It's one of the things. As soon as anything looks vaguely weird, Twitter just goes bananas, and people start noticing. Anyway, but yeah, I'll just briefly mention what happens with. If you lose the main site, that's that disk area showing 1000. If you lose that, you end up with a hyperswap. That's pretty exciting thing to happen. We have had one. It was a while ago. I'm not sure it's supposed to mention that. Oh, well, never mind. It's fairly public knowledge. We did have a real hyperswap, and everything just went over. I'm just thinking I've got anything there mentioned on my bullet points there. Yeah, just give it to talk about. So the whole idea is normally you've got traffic running through those sort of blue links. So you've got three blue links in there. But we've got the top Z talking over to the main disk we're talking about. You've got the bottom Z talking to the main disk. Both those Zs are active. They're talking in parallel sysplex. There's a thing about parallel sysplex 101 coming up later on in the week. And then what happens, we got a synchronous copy going between those two disk frames. So 1000, disk number 1000 is going to disk number 2000 on the other disk. Now, it needs to be a different number because both the devices need to be visible to the Z at the same time. So you basically have to, for each time you have a given disk, you have to lose two numbers to be able to support it because both need to be available at the same time. So if the hyperswap happens, you lose number 1000. I'm just going to blur over the whole note. Really clever stuff happens in GDPS code and ZOS code, and your two Zs on the left-hand side, no, they just pause briefly. Some software goes underneath, changes a whole load of bolts underneath the programs, and device 1000 is effectively replaced by 2000. 2000 is a totally synchronous copy. Now, to explain with synchronous versus unsynchronous. Okay, so if thinking back to when I was talking about doing those writes and doing those writes into memory, so program comes in and say, right, I want to write this lump of data to this area. Have you got it? Yes. The report goes back to the program. That would be normal. With a synchronous copy, it's a little more extended that. The two disk units know about each other. So you write over to the first one, writing to disk 1000 in this case. They said, okay, but it doesn't go back to say that everything is okay yet, because 1000 says, oh, hello, I'm in a PPRC or a Metro Mirror relationship with 2000. It talks to the other frame. The other frame said, yep, I've got it. As soon as that one comes back, that gets reported back to the original frame. So good, we're all good. Both sides are okay. Report back to the program. So that way, everything is kept in sync. Absolutely everything that gets written is written on both frames at the same time. That's a key point for how things are able to stay in sync and give you the high availability solution that you want. So as mentioned, you guys lose a 2000 and well, okay, the 1000, 2000 will catch up at some point. This happens. Or you lose the 1000 and you're looking at hyperswap and they start using those yellow links. You can see I drew in there, talking to device 2000 instead of 1000. Okay, hopefully that's explained enough about PPLC. I'm going to move on to the other part of the question, which is DR. So using some of the elements I had from the diagram earlier on, you need to have a DR site. This is probably not going to be news to any of you. Not going to start going about locations, but one of the issues that we certainly have is that synchronous replication I was mentioning earlier on, where it goes to the first frame, then talks to the second frame, and the second frame go back to the first frame before saying, yep, your IO is done. The time taken for those two frames to talk to each other over a fairly big distance is too long. Visually, the speed of light is basically too long because they're over fiber links that are all done by sort of optical communications. So as a result, it relies on the speed of light. The speed of light over the, let's call it 100 miles. It isn't, but for 100 miles or so, for a conversation to go 100 miles through light back again is a bit too long. Now, someone could probably work out what that is, so I should know, but it's certainly somewhere around a significant amount of time that means it gives us a practical problem. I think there was a test, some years ago, and thought, okay, well, theoretically, we could have a synchronous link, but it means that every transaction would have about 1/10 of a second added to it. And 1/10 of a second is an awfully long time in computing terms. I mean, looking at something like a banking application, that's more than you can pick up in practice. So synchronous theoretically could work, but because the speed light is too slow, you use asynchronous. So in our case, for the moment, we have XRC. We know XRC is on its way. It's going to be being replaced by GM. I'm not going to do too much of the difference between the two, but GM is effectively a frame-to-frame solution, but not doing the sort of the constant immediate conversations I mentioned earlier with synchronous. XRC is different in that it's actually run by software on the Z. So, as you see in the diagram below, we have a system data mover, which is sitting on a Z partition. And that, so it's no surprise I used orange. So I was talking about the numbers earlier on, being able to have systems that can talk to two different sort of disk units. This is the practical upshot of that from our point of view. So the system data movers literally look for the changes the whole time, pull the changes, what's going on location A. So your disk 1000, has anything happened to it? If it has, aha, we'll take that and we'll write that down onto another disk. Now, because STM is a Z partition, they can't have the same device numbers again. So in this case, I'm going to, because I used the example earlier on where I was able to use different numbers and or what appear to be the same numbers from the same controller, but aren't. They're on two different disk frames. This is where the practical upshot comes in. So the STM takes from 1000 and writes out to 1080. That's just a convention that it's actually a convention we use. These aren't the numbers that we use exactly, but the whole idea of having a hex 80 offset is something that we do use. I don't think I'm giving away too much with that. Anyway, so it searches for the data and writes it down. Now, one of the things that XRC does and that's particularly fun is the whole idea of keeping well, it's looking at loads and loads of different time. The getting of that information is going to come around effectively at different times as well. So it blocks off in different points in time, saying, right, hey, we've got all the updates for up to this particular point of time. Good, done. That is a group of disks. This group is consistent, hence the name consistency group. It does that again, then another lot of things come through. Right, we've got another consistency group, another time point, and it does that several times a second, which is quite impressive. So that's how that side works. Oh, it's really not odd having no feedback from people. Just imagine what you're thinking, which is strange for the old head. Right. Yeah, mention that one. So one of the key things, again, mentioned in here is the fact that we then use two more, or another device number, which gives us a bit of a problem later. So moving on, because we're talking about a four-site solution, there's even more numbers that are used. So on in the bottom right, we've got 2080 now appeared as another device that is required. So I'm just going to just check over incremental resync. So we have both high availability and DR solutions. Well, that's fine, but imagine you had a problem with your primary disk, 1000's gone. The STM saying, well, okay, is 2000 absolutely right? Or could you have stopped somewhere in between? How do we know that's actually right? Now, another way it knows that is right is using a thing called incremental resync. The system data mover is talking or watching both sides of the frames in the primary site. So if the primary, go that one down. I don't know if you can see the mouse, but if the frame that's holding 1000 has a bad situation and swaps, we have a hype swap situation. 2000 is in play. That's now the live version because we have a swap and go policy. I'm not talking about policies, so I'm going to let that go. But it knows it's so the SDM in the middle here knows that device 2000 is okay. And that's what incremental resync gives you. Otherwise, you'd be looking at effectively a full copy of the data, and a full copy of databases this big is not a good thing. Just explaining the right-hand side as well, because we've got the four sites. Effectively, you've got another copy of the high availability solution, but it's in the second location. So the practical use for that is when we run a regular test as we do to make sure that we can approve, yes, we can do a DR, we take it all over, we move everything over to location B, we run live in location B for a while. Well, while we're running in our DR location, we still want that high availability, because otherwise you're going to effectively a single point of failure, and that's not good. So that's why you effectively get that fourth site, because to give you the high availability solution in your DR location. You've also got the STM when you have moved over. There's an STM in the location A that sucks everything back so you can come back home again. But again, there's only so much you can get in one diagram. One of the other practical things that this gives us is when we're doing a DR exercise, before we start playing around with the primary frames, we can just say, okay, well, let's break that mirror. We know we're in a good place. We just break the two Metro mirrors, the PPRC side. That gives us gold copies. So we know where we are. We know we're happy. If the worst comes to the worst and everything goes horribly wrong, we can bring our systems back using those gold copies. And that helps you sleep at night, I can tell you. Anyway, what else? I covered everything I want to do there. Yes. Okay. So key thing at the moment, we're now up to 4 numbers for each device, which it's adding up, and I'm showing why. Okay. So we get some more because DB2 has extra special needs. Obviously, backups aren't going to be a surprise to anyone. No matter what shop you're in, you're going to be backups of some sort. Now, for DB2, there are a few things that really need to be kept in a good place. One of it is the speed. When you're taking a backup, if you were just taking tape offloads, by the time you got to the end of the the last volume you're backing up, it's going to be so far out of sync with everything else that's gone on, it's not going to work. It's effectively useless. So what we do is fairly standard thing. I think you'll have to ask a DB2 expert on this one, but effectively take a point-in-time flash copy. So every device in the SMS group for that DB2. Oh, I've got the sun come around into my eyes. That's slightly unfortunate. I'm going to be slightly sideways on for you for a moment. Every volume that's in that frame does it as an within frame flash. So in other words, then a copy is taken of every volume. Second one, right, is made there. At that point in time, it's exactly the same. Now, that copy itself would take a lot of doing, even in a fast frame, because you need to make sure that flash is consistent across every single volume. You're effectively taking a little pause in processing, say, right, do a flash now, and they all do a flash. However, doing the full flash over every disk, that's too slow. So, but everything's handled by bitmaps. You say, right, it's a flash point here. Let's make a note where all bitmaps are and keep processing again. So then in time, the flash copy said, right, well, where would I have been if everything was absolutely in sync? So it does that. So eventually, that makes it sound like a long time, but after a while, you've effectively got your primary volume and you've got a second copy of that primary volume. You can then take that, and we also then offload that to tape. This is, and that's well documented elsewhere. And if you're a DB2 shop, that something like that will not be a surprise. So speed is absolutely vital for that, because that moment of just going flash does stop processing briefly. It's really quite a quick one, but it's not insignificant. With our application, any impact on time needs to be considered fairly seriously. Anyway, there's ways of making sure that flash is good. One of which is making sure that the flash copy is in the right location. The best place for your flash copy is within the same control unit. Next best, at least be in the same rough area of the frame. Now, I haven't mentioned that effectively the frame is sort of in two halves. I'm not sure how much that actually matters too much, but just take it for the moment that having a flash copy in roughly the same area of the frame is not as good as being on the same controller unit, but better than being elsewhere. And again, theoretically, if it's in the other half of the frame, well, okay, there's loads of comms going on. It'll work, but it's not good. So the best option is to keep it in the same control unit if you can. So the practical upshot of that is where we had 4 volume numbers being taken up for each device. That's now just gone up to 8. Reason being, why isn't it just the 1? Well, okay, in some of the test environments, it is just 1. However, for a production database, you need to take backups no matter where you are. So you need your backup in your primary frame, your A1 frame. If you've done a hyperswap, you still need to be able to back up. So you've got to have those devices in your A2 frame. Likewise, if you're running at DR, you've got to be able to take backups when you're over running a DR. And similarly, if you have a hyperswap, if you're over there, you've got to be able to run backup. So it's got to be 8 frames. For every volume or named volume in the DB2 database, you're effectively now saying you've got to have 8 physical volumes that it relates to. This keeps adding up, doesn't it? So, a quick little bit of fun with some. So, again, the database, this is a theoretical thing. The database isn't 248 base devices, so we're just going to use this to have a play with some of the mathematics involved. If you've got 2048 volumes, like our number 1000 we had earlier on, with all those 8 copies that you actually require, that means your whole database is going to be, let's say 16,384. But that, if you think, easy to think of it in hex terms, it's effectively, it's going to be full 0, isn't it? Yeah. A quarter of all the total numbers that are available. Well, actually taking a quarter doesn't sound like much, but it does start adding up. When you think, well, okay, it's important, but there are going to be other databases that are in there. So just to run SAP, there are at least another 2 databases that you want in there at the same time. So that's taken up some extra space. the operating system, that needs some space. So you think of all the extras, the things that you just having your system packs, or somewhere to put jez, everything like that. That needs a certain amount of space. I think I've listed some of the other bits. So yes, the things like image copy pools and stuff like that's what DB2 needs. Well, yeah, there's 2 lots of those as well. Various transient sort work areas. There's loads of them. Right. Similarly, all your GDPS systems, they've also got. They also need their own operating system. They need space in which to work. That takes up numbers as well. So you start getting a bit squished, and then you also get the idea that things grow. So there's BAU growth on a regular basis. Well, that's growing time on time on time. When we first put this current solution in some time ago now, it was okay. It fitted quite nice and easily. We've got an awful lot more disk now than we had when we first put it in. It starts getting quite big, and have to. Well, one of the things I have to do is work out where we're going to put all the devices, and what numbers are we going to give them. So that's a fair amount. Then you get migration activity. That can be quite exciting. With the last migration, I was told to prepare for the databases to grow to 3 times their current size. Well, hang on. If it's already taken a quarter and it wants to be 3 times the current size, well, you can imagine I didn't sleep particularly well until very early one Sunday morning. I worked out how I could do something to involve more using the numbers. So some of the techniques I mentioned were the things that came up in the wee small hours. Oh, yes, and with the next one that's coming up, when we go from XRC to GM needs a whole nother lot of device numbers, because its own journal volumes takes up another number within the frame. So yeah, there are a few challenges coming up on that one. So how am I doing for time? Oh, doing okay. So one of the key things I want to then get in the idea is there are limitations, but also ways around it. I'm going to get back to numbers and how we can solve these things. So a device number can be used. You're using up lots of numbers, but you can also reuse numbers elsewhere to give them a different context. So going back earlier to our example, remember it's all color-coded systems. I hope you can see my mouse there. You can have in this table here, you can see we've got those 4 device numbers that I mentioned earlier on. What you could do is reuse them. So, remember I had 1080. I was using that as a replication target for XRC. Well, actually, I worked out, this was the one very early in a Sunday morning. I worked out the STM doesn't need to be able to see the flash copy. We don't need to replicate that flash copy. So we can reuse the same number. So that's why you then get 1080 is available on the blue section on the left-hand side of that table. So you got your main, the main device number one, number 10,000. No, 1,000. What am I talking about? The number 1,000 on control unit 10 is 1000 effective, isn't it? Yeah, sorry, wittering away. But so that can be your main data doing all the reads and writes you're expecting. Then you can have 1080 for your DB2 flash copies. This makes keeps it nice and efficient because it's close by. That's okay. That same number 1080 can also be used over on frame B1, where the SDM is taking all your main application data and it's plonking it back over onto another frame. But because it doesn't need to see the other, it can reuse the same number. So if you have to spend a little moment looking at this one. So each frame can potentially use all those numbers. Okay, I'm only up to 3 at the moment. At the moment, it's only 2 because I haven't actually implemented the GM journals yet. But again, that's one of those wee small hours I worked out I could do this. The GM journals can take on another number, but on each frame, you can use 3 of the 4 numbers and reuse those 3 of the 4 numbers, which means your original maximum is being extended by the use of clear application. So yeah, on the right hand side you can see an idea of which one's talking where. So yeah, your application systems talk to a primary disk there. They can see their own MetroMirror copy and the flash copies on each one. Whereas the system data mover is not looking at flash copies at all. It's just doing source and target replication, and also having its MetroMirror copies, because it's got MetroMirror itself. And it's also allowing for incremental resync reference. And similarly, you've got your over in the far site, it's using things. The numbers are slightly the other way around, but functionally they're doing roughly the same thing. So just make sure I've got everything across there. Oh yes, some other obviously the case system. Also useful. The case system don't use those flash copy devices. Well, not yet. That's another thing that may or may not be coming. But it's also the only way to access some of the flash copy devices remotely. So, for example, if you're adding some more disk in, let's say we have 1001, well, you need to be able to initialize everything. If you haven't got a system over there in your B region, well, how are you going to initialize it to make sure it's ready for when your DR comes over? You're not going to do a DR access. Oh, sorry, before we use it, they've got to initialize a whole load of volumes. That won't go down well. So because the case systems can see them, that's where we do that sort of a work. So that's how that all works around there. Good. I think I may just say the next slide I've got to come up is one for any questions. It's all gone very quiet. Chris hasn't said a thing. I may come back to this slide in a moment so people can mull over it or ask questions around it, because that's more likely where it's going to be. But I think we've hit the any questions side of the presentation. So I don't know if you're have I sent you asleep yet, Chris?
No, I'm here. I'm still wide awake.
Good.
Yeah,
We've got a few.
Give it a couple of minutes for some questions then, just in case any come in through the chat.
Okay.
We'll give it a couple of minutes. But no, thanks for that, Simon.
Okay.
Brilliant.
Fair enough. So if I can go on a bit, in which case, rather than actually say any questions, we'll do that, and we'll pop it forward onto the session feedback form should anyone have anything.
Yeah, and I think we're going to stick a link in the chat as well for feedback, just so people don't have to type that in. There you go. Yeah, David's just put a link in the chat. So if you could offer some feedback, that'd be brilliant. So yeah, we'll give it a couple more minutes just in case there's any questions.
Good stuff. Well, while we're waiting, we can also mention the charity raffle. There you go.
You could give us your Brian Blessed impersonation, Simon.
Oh, I haven't done anything like that. Anyway. I've got tweed. It's at least a start, Not that I'm going to start climbing up Everest or anything like that. I think I've been talking to her. I haven't got the voice for her at the moment.
Your Flash Gordon impersonation. I'll get you some good feedback.
Oh, here we go. We've got something in the chat. I can see the chat now. There we go. Oh, JT's been around. Oh, I wish I knew the context of that one. Never mind. I'm sure James will tell me at some point. He's still there. No, there he is. Yeah.
You can unmute. Simon.
Right. Well, I think either everyone's understood or I've stunned them into an early sleep.
Yeah, no, I think we're happy to wrap it up there. We've given it some time for questions. So yeah, thanks again, Simon, for presenting. So yeah, that's brilliant. Yeah, thank you. The next 102 session, guys, is RACF for Sysprogs 102, which is being delivered by Mark Wilson at 9 o'clock on Tuesday. But yeah, thanks for joining, and I hope to see you all next week. And yeah, thanks again, Simon.
Yeah. Yep, that's the end of the slideshow. So there you go. Right. Oh, thank you very much, Beth NJ. Much appreciated. So you do the close down at this point, or?
Yeah, closing now.
Bye all.
See ya.